All right, guys, so we're carrying on with Learning Guide 6, and Lesson 3, we're talking about related rates. So we're kind of switching gears here a little bit. In the previous previous lessons, we were talking about position time graphs. We were talking kind of all about graphs and particle movement and that kind of stuff. We're going to use the same idea of derivatives and use the same idea of time, but we're not just looking at particles anymore. So you'll see what we're talking about. And again, it's kind of cool because you can see how to apply this in a real life situation in this learning guide. Now, I'm not going to lie to you. This is going to be a long podcast. And the reason is because we're going through word problems. That is going to get very boring for you. So I really encourage you to pause, fast forward. Don't sit and listen to the whole thing. Otherwise, you're just going to tune out. So when I get to a problem, just pause it, try it yourself, and then fast forward, see if you get the answer. If you don't, then maybe go back and listen to the podcast to make sure you understand. Now, again, this lesson actually, it started off as being I was most scared to teach this one because it's pretty intense and I don't know, I didn't feel all that comfortable with it. Now it's definitely one of my favorite because I've kind of come up with maybe a little bit of a shortcut, I guess, or some kind of formula that you can kind of do for all of these questions. So I think you're really going to like it. Just give it a chance. It does seem pretty tricky at the beginning, though. Now, the first thing that we're going to talk about is, okay, what kind of problems are we going to see? So many variables in our world change based on time. This is the big one. So population over time, medicine over time, sales over time. And the questions that we're going to do, we're going to look at them over time. A lot of the questions that we're going to do actually involve geometry. So area and volume normally are written in the terms length, width, height, base, radius, but not time. Therefore, related rates, which is what I was saying we're going to be talking about in this lesson, require our old friend, implicit differentiation, with respect to time. Now, if you look at implicit differentiation, you have no clue what that is. You may want to look back in some previous learning guides. But basically, just a quick summary of it, it's when we have more than one variable and we need to take the derivative, a lot of times using the chain rule of each derivative. Okay, so let's look at the first very basic example. What would the following function look like using implicit differentiation with respect to t? So that last part might be a little bit confusing. So first of all, I know that my y, I can't just take the derivative of y and be done. I have to use the chain rule here. So 2y, and then remember every time we have a derivative of y, we need to include normally dy dx. But in this case, because it's saying with respect to t, instead of dy dx, this is now going to become dy dt. Okay, so everything is in relation to time. The 3 is going to disappear, and then obviously we have that 3 times negative 2. Now, normally what we would do is just say negative 6x squared, and then we would be done with it. But because this is respect to t, I also have to include dx dt. So everything has to have that implicit differentiation badge on it. We've got to put everything in regards to t. Okay, in relation to t. All right, so how to solve related rates. Now, this is not going to make too much sense to you at the beginning, so I really encourage you to come back to this page. It's actually a really helpful page, I find, because you can just kind of follow step by step by step what to do. So we'll just read through it quickly, and like I said, come back to it if you are having some trouble. So number 1, draw a diagram if there's not one there for you. Take a snapshot of what's happening and label all of the known and desired variables. So basically draw a picture and label it. It's going to help you. Number 2, relate known and desired variables using formulas. Then when I say formulas, I literally mean, oh yeah, a is equal to base times height divided by 2 for a triangle, or a squared plus b squared equals c squared. All of those formulas that you learned back in the day, those are coming back out. Okay, you're going to be using them again. Substitute only fixed unchanging variables into the formula. That's not going to make any sense to you just yet, but you can go back to that and it will. differentiate with respect to time, which we just talked about, and then substitute changing values and rates into the differentiated expression. These two steps are really helpful, and again, I'm going to come back to them a little bit later. Example number one, now this one, we can kind of skip the first step. We don't need to draw a diagram. There's no diagram needed here. But basically, and our formula has already been given. Okay, what we're doing is basically finding the derivative according to time, with respect to time, of this and actually solving this. So I actually really like this question because it shows kind of just the derivative part of it. All right, so it's saying if x cubed y cubed equals 8, and the derivative of x with respect to time is -3, find the derivative of y with respect to t when x equals 1. All right, so let's figure this out here. Now first we want to take the derivative. This is kind of like our UV, our product rule, right? So I'm going to take the derivative of y, which is going to be 3y squared, and then remember dy over dt, we have to make sure to include that, plus y cubed times the derivative of x. So that's going to be 3x squared, and then dx over dt is going to just be equal to 0. Okay. Next one, let's just simplify. Let's make this look a little bit nicer. So 3x cubed y squared dy dt plus 3x squared y cubed dx dt is equal to 0. Now the question is saying find dy dt. Okay, so we know dy dt, but we also know a few other things. We know that x is equal to 1, and we know dx dt is equal to -3. So let's substitute that stuff in. So I've got 3 times 1 cubed y squared dy dt plus 3 times 1 squared y cubed times -3 is going to be equal to 0. Now, again, let's simplify. So that's just going to leave us with 3y squared dy dt plus 3y cubed, never mind. No, I lie. Let's multiply these. Let's simplify them. So that's going to be -9 y cubed is equal to 0. We'll just simplify it all in one step here. Now, I want to solve for dy dt, but you'll notice that we still have a y in there, and we can actually solve for y. And this is something you're going to be able to do in some next a few questions as well. If we take a look up here, I know that y cubed is going to be equal to 8 divided by, so y cubed is equal to 8 divided by x cubed. And we already know that x is equal to 1. So y cubed would be equal to 8 over 1, which is awesome. So y cubed is equal to 8. The cube root of 8 is 2. So y must be equal to +2. So let's substitute that in so you can see that we can kind of go back, use our question to help us out. We're going to be doing that quite a bit. 2 squared, and then we've got dy dt minus 9 times 2 cubed is equal to 0. So now I've got 12 dy dt minus 72 is equal to 0. So add 72, divide by 12, so dy dt is going to be equal to +6. All right, so here you can see a nice first example on implicit differentiation. All right, let's move on to example number 2. This is what you're going to be seeing the majority of. Shapes, geometry, formulas, that kind of stuff. All right, so example 2. The length of a rectangle is decreasing at a rate of 1 centimeter per second. So you can see that I'm talking about the length, not as just L, but I'm talking about the length as almost like a speed or a velocity. This is related to time. And the width is increasing at a rate of 2 centimeters per second. Find the rate of change of the area at the moment where both lengths are 10 centimeters. So it's not saying find the area, it's saying find the rate of change. And the rate of change means that I'm talking about the area, dA over dt. So what is our area with respect to time? All right, so if we go back to this kind of handy strategies, and I'm only going to do this once, and then you guys can go back on your own. Number one is saying draw a diagram. Take a snapshot of what's happening and label the known and desired variables. So we're talking about length and width here, right? So that's going to be our length and this is going to be our width. But what it's saying is that the length is decreasing at a rate of 1 centimeter per second and the width is increasing. So if I were, again, to take a snapshot of what's happening, this would be the next rectangle. Then it would look like this, right? Because the width is increasing and the length is decreasing. Okay? So first, we're just getting a picture of what's happening. Label the known and the desired variables. Relate them using formulas. So this one I'm gonna skip for 1 second. And what I'm gonna ask us to figure out is what are we looking for? So first of all, the length, we know dl over dt is going to be decreasing at a rate of 1 centimeter per second. Now, the word decreasing is very, very important. Am I just going to write 1 centimeter per second? No. Decreasing means I have to put in a negative there. So all of the speeds are related to the word A. So you've really, really got to be careful there. Okay? They're actually related to the origin, which we'll get to in a little bit. Now the width is increasing, so our dw over dt, so our width is increasing at a rate of 2 centimeters per second. So obviously that one's going to stay as a positive. And then underneath that, we're going to put dA over dt, and that's what we're looking for. And it's saying what is, or find the rate of change of the area at the moment when both lengths, so the length and the width, are each 10 centimeters. So I'm actually going to write that in here. When length and width equal 10 centimeters. This, what I just did right here, I really encourage you to do. That's kind of the way that, I don't know, I've just started doing that. It makes the questions way easier. You can kind of figure out in a very organized fashion, what am I looking for? What do I have? Okay, so now I'm going to go back to number 2. It's saying relate known and desired variables using formulas. Well, guys, we're talking about the area of a rectangle. We all know the area of a rectangle is length times width. Okay, so that's good. Now if I go back, number 3, substitute only fixed unchanging variables into the formula. So any fixed unchanging variables. Well, a lot of you guys might be tempted to put in the 10 right away because you're like, oh, okay, well, length and width are 10, so it's the area. We cannot use this information because, or yet, I should say, until we actually take the derivative. So this is, what is the derivative of A over the derivative of T, or the my change in area over time? When it's this is after my derivative, and we're always going to wait until we take the derivative. So right now there is no lengths and widths or anything that's not changing. So there's no numbers actually that we can put in. Okay, so number 3, I just have to skip. Number 4, differentiate with respect to time, and then substitute changing values and rates into the expression. Okay, so that might not make sense, but what this is saying is find the derivative. Okay, so that's going to be easy enough. dA over dt. This is like my u and my v, product rule again, remember? So that's going to be length times the derivative of w with respect to time, and then width and the derivative of my length with respect to time. Now, guys, and I'm going to say this quite a bit, now that you've taken the derivative, everything is fair game. I can put in whatever I want into my equation. That's the key. So we're looking for dA over dt. I'm just going to switch colors here. So dA over dt, and we're going to plug in everything. Now length, everything's fair game. So length is going to be equal to 10. My dw over dt is going to be 2. W, again, is going to be 10. And dl over dt is going to be -1. So again, we've taken that derivative. Everything is fair game. 20 minus 10 is going to leave us with 10 centimeters squared per second. Again, because we're talking about area over time. And that's it. Okay, so if you guys could follow those steps, these questions are not that bad. All right, let's take a look at the next one. Sand is poured by a conveyor belt at a rate of 2 meters cubed per minute, forming a pile in the shape of a right-angled cone, where the radius is always twice the height. How fast is the height changing at the moment when the height is 4 meters? All right, so the first thing that we want to do, remember, is draw a diagram, which obviously this one is done for us. And then we want to start writing in, our variables and that kind of stuff. Now, first it's saying, like, we've got a radius and we've got a height here, obviously. But one thing you guys want to make a note of is that you don't want to be using a lot of variables, because a lot of variables equal a lot of derivatives and a lot of things that we need to substitute in. So you always want to limit your number of variables. It's saying that the radius is twice the height. So radius has to be twice the height. Now, obviously, this diagram is not to scale, but use your imagination. The radius is twice the height. So instead of radius, r, let's use 2h. Now what we're going to do is that little, organized thing underneath that I was talking about. Sand is poured by a conveyor belt at a rate of 2 meters cubed per minute. This is obviously talking about our volume. So underneath here, I'm going to start to organize things. dv over dt is going to be equal to 2 meters cubed per minute. Okay. Forming a pile in the shape of a right-angled cone, where the radius is always twice the height. So we've used that info. How fast is the height changing? So we know how fast is the height changing. What we're actually looking for here is dh over dt. So what is dh over dt when the height is 4 meters? So when h equals 4 meters. Okay? And remember, this here, use after derivative. We can't use it yet. All right, so the next step, we've labeled our diagram, we figured out what variables we need. Next thing is we need a formula here. Now, we're talking volume and we're talking cone. So remember, the volume of a cone is equal to 1 over 3 pi r squared h. Now, please keep in mind what I'm telling you. If you can limit your number of variables, do it. Now, one hint that you want to keep in mind is looking at the question, it's saying how fast is the height changing when the height is 4 meters. Obviously, this is dealing with height, so we need to keep h in our equation. I don't really care about r, nothing's talking about r, but h is quite important. Well, luckily enough, we said r is equal to 2h. So let's rewrite this. 1 over 3 pi, and then I've got 2h squared h. Now look at, I've taken out a variable and we're able now also to simplify. So our derivative is going to be so much easier. Now let's do that. So volume is going to be equal to 1 over 3 pi times 4h cubed. Let's again simplify. So now I've kind of got like a 4 over 3 pi, which is just a number, a coefficient, and then h cubed. Okay. Now there's no more simplifying that we can do. So the next step is we want to take the derivative of this, okay, with respect to time. So dv over dt equals, this is a coefficient. So basically I'm taking that h cubed, I'm timesing the 4 over 3 pi by 3. Okay, so I'm timesing that by that, which is obviously just going to result in 4 pi. And then I've got h squared. And then I need to take the derivative of h, which remember was dh over dt. Now that I have taken the derivative, everything is fair game. I can plug in everything that I've got here on the left-hand side. So dv over dt, we know is 2. 4 pi h, remember, was 4 squared. And we're looking for dh over dt. Now simplify. So I've got 2 is going to be equal, I've got 4 squared times 4 is going to give us 64 pi, and dh over dt. Again, basically I'm going to have my dh over dt is going to be equal to 2 over 64 pi, and that would just simplify to 1 over 32 pi. And for units, this is my height over time, so it's just going to be meters per minute, nothing squared. And that would be our final answer. Okay, so now you definitely should be at the stage where you want to be pausing and fast forwarding, because I'm probably boring you to death by now. So pause, fast forward if you haven't been doing that already. All right. Example number 4, a coffee filter has the shape of an inverted cone. The radius is 8 centimeters at the top. The filter's height is 10 centimeters. Water is drained from the filter at the rate 25 centimeters cubed per second. How fast is the depth of the water decreasing when it is 5 centimeters deep? Now, a diagram is really going to help here. And we've got some stuff that's not moving, right? The radius is 8. That's not moving. And it's saying the filter's height is 10 centimeters. That's not moving. What is moving is it's saying water is drained from the filter at the rate of 25 centimeters cubed per second. How fast is the depth of the water decreasing when it is 5 centimeters deep? If we kind of visualize what's happening here, we've kind of got like a new cone that's kind of being created, right? Like I want you guys to imagine that water is coming out, and if the water is drained, I just picked that random spot, that's what the new cone would look like, right? All right, so let's kind of organize what we've got so far. It's talking about our volume, so our dV over dt, and it's draining, which means that we've got to have a negative 25 centimeters cubed per second. And it's saying, how fast is the depth of the water decreasing? So we're kind of looking at H here, okay, when it is 5 centimeters deep. So we're looking at dH over dt. What is the rate that the height is decreasing when the actual height itself is 5? And remember, we take this after derivative. Okay, don't forget. All right. Now, in this question, what a lot of you guys would probably do is start writing the volume of a cone. Now, that's actually not going to help you here, unfortunately. What you actually want to be doing is recalling the similar triangles. Okay. Now this is something, I shouldn't say that the volume is not going to help you, because of course that's obviously what we're going to be using, but you're not going to have enough information in order to use that formula just yet. If I look at that formula, 1 over 3 pi r squared h, we need to limit the variables, right? So we don't want an r and we don't want an h both together because we already have a v as well. I mean, kind of maximum, I always tell students, like you should have 2 variables normally. We want to get rid of something here. Now, obviously, h is in our question. Therefore, it makes sense to try and replace the r, just like what we did in that last question. So if I look at how to do that, it's a little bit trickier than the last one, because we need to think again about similar triangles. And similar triangles are basically relationships between 2 triangles that we've got. So right now I've got an R and I've got an H, and we also have a little, a little triangle here, which is our R and our H. And here we've got an 8 and a 10. So my radius is 8 and my height is 10. And we can solve solve for r by looking at our cross multiply and divide here. Okay, now remember, some of you are going to be really tempted to put in h is equal to 5, right? I'm sure some of you have made that mistake already. So h is equal to 5, don't forget, that's why I keep saying after your derivative. You cannot use that 5 until we take the derivative. So if I cross multiply and divide, I know that r is going to be equal to 8h over 10. And if we simplify that, obviously 4h over 5. Now I can substitute that into my equation. 4h over 5 squared times h. And it looks like I've made it harder, but in fact we've limited our variables, so it's definitely going to be easier. So let's simplify this. Volume is going to be equal to 1/3 pi times 16h over 25 times h. Volume is going to be equal to 16 over 75 pi times h. Oops, sorry, I forgot my squared there. H cubed. Okay. And now taking the derivative is quite easy because, again, 16 over 75 pi is just a coefficient. So I'm just, again, multiplying 3 by that. So I've got my dv over dt equals 16 pi over 25 h squared dh over dt. Now that I have taken my derivative and simplified, everything is fair game. So dv over dt was negative 25. 16 pi over 25. H, remember we said, was 5 squared, and then we're solving for dh over dt. So you can see how this all comes together really nicely. Simplified, negative 25 is obviously just going to be equal to 16 pi because those are going to cancel. dh over dt. So dh over dt is going to be negative 25 over 16 pi centimeters per second, because again, we're talking about height. And now if you get a negative in your answer, you don't just want to be like, oh, okay, great, it's a negative. You want to think, does that actually make sense? So go back to the question and you say, okay, how fast is the depth of water decreasing? So obviously if it's decreasing, a negative rate does absolutely make sense. So we've got our negative 25 over 16 pi. Okay, so guys, one thing you want to look at in this question, because you're going to see quite a few of them, if you have two triangles, chances are you're going to use similar triangles. Okay, that's pretty much a safe bet in these questions. And again, something that I keep mentioning, you want to limit your number of variables. So anytime that you have a formula like this with 3 or more, you want to think, how can I replace something so that we limit that number? And in order to replace them, you just have to remember what's going to be in the question. So notice how h was in the question. So obviously we don't want to get rid of h in our formula. Okay, so just a couple of things to summarize. All right, now the last example, again, this one is not as hard as the last one. So if you kind of cheated and just listened to the solution for the last one, I really want you to pause and try this one yourself because you're definitely going to get it. All right, example number 5. Air is being pumped into a spherical balloon such that its radius increases at a rate of 0.75 centimeters per minute. Find the rate of change of its volume when the radius is 5 centimeters. So we've already got our diagram here. Let's do what we've been doing before and organize our information. So the radius is increasing. So dr over dt is going to be 0.75 centimeters per minute. Find the rate of change of its volume. Okay, when the radius r equals 5 centimeters. And remember, this we know not to use until after we take the derivative. So the volume of a sphere, some of you may need to look back on some formula sheets for that one. Volume is equal to 4 over 3 pi r cubed. Now in this one, you just ask yourself, okay, do I have too many variables? Well, no, because we are looking for dv over dt. We've got an r, and we've got a dr over dt, so we are good. All we have to do is take the derivative. So dv over dt is equal to, now remember, it's basically this times this, so it's going to become 4 pi r squared dr dt. And we want to substitute everything in now. So we've got our dv over dt, which is what we're looking for. 4 pi r, now we can use it because we've taken the derivative. Dr over dt, so that's going to be 0.75. We want to simplify everything. Okay, so our dv over dt, guys, this is just calculator work. You're going to get 75 pi centimeters cubed per minute. And that is that. All right. So please, please, please try the homework, 3.5. Make sure you go see the help desk if you have any questions with this. You've definitely got to practice because this is going to be all over your assignment and your test. Okay? So good luck.